My name is Mounah Honore Cesaire. I'm a PhD student at INRIA in France, and today I'll present you my work on the impact of kernel asynchronous APIs on the performance of a kernel VPN. First, let's start with some context. This work is about VPNs, and here VPN stands for Virtual Private Networks. VPNs are network applications that are used to anonymize internet users. Basically, users have their network traffic encrypted and then sent to the VPN server, which will serve as a proxy to preserve their anonymity. VPN is a very widely used application with a big market share. In 2025, the market share of VPN is estimated at more than $68 billion, and it is expected to be more than $200 billion by 2030. Also, the number of VPN users is quite large. It is estimated that more than 1.75 billion of users people use VPNs, which represents about 30% of all the people using internet nowadays. WireGuard is a recent VPN protocol built into the Linux kernel. It leverages multi-threading and implemented as a Linux kernel module to make it very fast. But there is a question here about its scalability. Is WireGuard a multi-threaded VPN kernel module able to really handle thousands of clients efficiently? To answer this question, we stress test WireGuard with up to 1,000 clients, generating a total of 25 gigabits per second of network traffic in both upload and download cases to a VPN server that has 25 gigabits per second network card and 80 cores Intel CPU. We measure the forwarded throughput traffic that the server is able to handle and the corresponding CPU usage. The results are quite surprising. When clients perform download, the server scales well. This is shown here in the line in red, which scales linearly up to 21 gigabits per second. However, for uploads, represented here in the line in black, it peaks at only 12 gigabits per second with 500 clients, and then actually decreases down to 4.5 gigabits per second as we add more clients. Even more puzzling, CPU usage never reaches 1000% even with 100 clients, contrary to the download use case. Here, for example, we have one core that is used at 100%, while the other cores are used at less than 25%. So this tells us something crucial. Neither the CPU nor the network interface is a bottleneck. So what's really going on? To understand this problem, let's first take a deep dive on WireGuard Linux kernel implementation. As stated in the context, WireGuard performs mainly two kinds of operations: encryption and UDP tunneling. Also, to optimize the network throughput, it relies on generic segmentation of loads and generic receive of load. It also uses many asynchronous APIs. Work queues, which is a kernel mechanism that lets tasks be executed by a fixed pool of worker threads, usually one per CPU, and software interrupt context. All these are operated through two main pipelines, transmission and reception pipelines. For the transmission, here, when packets are said to be transmitted through the WireGuard interface, they are first segmented using JSO, and then each chunk is encrypted and then encapsulated before being sent to the network. The segmentation is done as a net device callback, which is called when initiating packet transmission. Encryption and encapsulation are executed in work queues. For reception, when a WireGuard packet comes to the WireGuard interface, it is first encapsulated, then it is decrypted and recombined using GRO. The encapsulation is executed as a UDP socket callback. The decryption functions are executed into work queues, and the GRO in case of IRQD, which here stands for which here corresponds to the software interrupt context. The GRO is executed in software interrupt context because in the Linux kernel, it is the default execution context, and WireGuard developers just kept it like this. All these operations, both for the transmission and the reception pipeline, are all done asynchronously. Now that we have a better understanding of WireGuard, we systematically investigate multiple potential causes. First, as UDP encapsulation and GSO are done through network stack callbacks, we looked at network packet distribution across CPUs. Here we have the network interrupt distributions across all the CPUs, all the CPU cores, and we see that it is quite well distributed, which is because of RSS. Also, the choice of running decryption into work queues is unlikely the problem because in the transmission pipeline, which scales well, we have the encryption functions and the encapsulation functions that are executed into work queues. So the problem lies elsewhere. The root cause is what we call execution order inversion, EOI. Basically, in an ideal pipeline, stages should execute in order. Early stages complete before later stages begin. For example, decryption should complete before recombination. However, due to their priority, the recombination function, which is executed in software IRQ, is executed before decryption because software interrupt context has higher priority than work queues. There's thus a mismatch between the priority of execution contexts and the function execution order. And this can affect negatively the performance. To better understand it, we model a simple case. We consider a job done by three functions, F1, F2, and F3, each representing a stage, with each of these functions running in their corresponding execution context, G1, G2, and G3. Here, there is a dependency between functions. F1 must run before F2, which also must run before F3. As the execution contexts are asynchronous, however, corresponding functions can run in different orders. The optimal case is where the execution contexts are scheduled in the same order as the functions. The latency in this case is thus minimal and the throughput maximal. However, when the jobs are unordered, for example, here we have F1 and then F3 before F2, and afterwards F3. The first time F3 is called, it is interrupted, and it doesn't do any meaningful work, which means that here CPU cycles are wasted, and the latency to process this job is increased. The throughput will also be globally reduced because we take more time to process each job. In WireGuard, a soft IRQ, as I said before, a software interrupt has inherently more priority than work queues. This happens, and it happens quite a lot of times. I mean, it happens 80% for 80% of all the packets. EOI thus increases latency and decreases throughput. This also has some indirect effect on the scheduling of GRO functions across cores, which creates CPU imbalance. So to reduce the likelihood of EOI happening, we propose to run GRO at the same priority as decryption to preserve function execution order. To do this, in Linux kernel, we consider two alternatives to software interrupt context. First, kernel threads, because it is easy to deploy, and as this option already exists in the Linux kernel. To enable WireGuard GRO functions to run in kernel threads instead of soft IRQ is just done by modifying one configuration file. Secondly, we consider work queues because all the functions already run in work queues. This option, however, is not readily available in the GRO API, so this requires both kernel and WireGuard changes to support this. We evaluate the two options against the current version of WireGuard that we consider as the baseline. The evaluation setup is the same described earlier in the introduction, just that on top of forwarded throughput and CPU usage, we also measure the tail latency. The results show that for throughput with kernel threads and work queues, we improve the performance of WireGuard. Kernel threads, here lines in red and green, improve the throughput by a factor of 2.8, while work queues, here the line in blue, improves it by a factor of 4.17. This can be explained by the fact that with kernel threads, each GRO function has its dedicated thread. However, in WireGuard, in the server, each client has its dedicated GRO worker. Thus, with 1,000 clients, there's also 1,000 threads, which is a non-negligible scheduling overhead on a 80-core CPU with migrations and context switches happening more frequently. Regarding CPU usage, we observe that the corresponding CPU usage is way better than the baseline. Now the CPU is fully used. And for the latency, we observe that both kernel threads and work queues perform significantly better than the baseline. Work queue reduces latency by up to 46% and kernel threads by 65%. Also, tail latency in the download use case is slightly improved with kernel threads. In conclusion, this work shows that when designing a multi-threaded asynchronous application, reducing the likelihood of EOI happening with the right choice of execution context is crucial. Thank you for your attention.